Bismillahirrahmanirrahim. Assalamu alaikum. My name is Maryam Akhtar and I am from the Department of BS Chemistry. My ID is 004 and this is the course of Industrial Chemistry. And the topic that was assigned to me was of nitrogen-based inorganic compound, and this presentation is submitted to Sir Hizar question. So, first of all, I'm going to talk about my presentation layout, which consists nitrogen, nitrogen-based inorganic compounds, introduction to nitrogen-based inorganic compounds, ammonia, its manufacturing process, and the application of nitrogen-based inorganic compounds. So let me take a start from the nitrogen. Nitrogen is basically the chemical element with the symbol N and the atomic number 7. It was first discovered and isolated by the Scottish physician Daniel Rutherford in 1772. Many industrial important compounds such as ammonia, nitric acid, organic nitrates, and cyanides contain nitrogen. There are different forms of nitrogen, which include inorganic and organic nitrogen. Inorganic nitrogen include ammonia, ammonium nitrate, nitrite, all nutrient but toxic at high level. Living organisms and their proteins, nucleic acid, urea, and the other nitrogen molecules. So, what are nitrogen-based inorganic compounds? Such inorganic compounds which contain nitrogen are known as inorganic nitrogen compounds. Inorganic nitrogen is subdivided into ammonia and nitrates compartment, enabling the distinction between new and recycled primary production. These examples include ammonia, hydrazine, ammonium, hydroxamide, nitric acid, nitrate, and nitrate. So these all are the structure of the nitrogen-based inorganic compounds. This is ammonia, this is nitrate, this is ammonium, this is hydrazine, this is nitric acid, this is nitrate. So, first of all, I'm going to talk about hydrazine. Hydrazine is an inorganic nitrogen-based inorganic compound which are naturally produced by some yeast and open ocean bacterium. So it is of great economic importance because hydrazine is commercially available as an active solution in the form of salt, and hydrous hydrazine is only produced in very small quantity for a special application in satellite technology. It can be prepared by bioprocess and enriching process. Its application includes as it play a key role in organic synthesis, pharmaceutical, and pesticides. So let me talk about nitric acid now. Most of the nitric acid is utilized in the form of 50 to 70% of fertilizer, so it is of great economic importance. In its manufacturing process, it includes direct process or swart process. Its applications includes ammonium nitrate, which is very explosive, oxidizing agent in glass and animal industries. Nitric acid is also used in the digestion of the raw phosphate. So now I'm going to talk about hydroxylamine. Hydroxylamine is an inorganic compound with the formula hydroxyl, NH2OH. It can be prepared by racking process, nitrogen monoxide reduction process, nitrate reduction process. It is of great economic importance because it is used as a reducing agent in the manufacturing of the enzyme for the use as skin prevention agents. The pure material is white, unstable crystalline, and hygroscopic compound because it absorbs the moisture from the environment. It is used in the paint, pharmaceutical, and pesticides. Now, this is the turn of the ammonia. It is of great economic importance because 85% of the worldwide production is utilized in the manufacturing of the synthetic fertilizers. Ammonia is an important primary inorganic material. It can be produced from the Haber process and modern method. Now, I'm going to talk about the manufacturing process of the ammonia. It can be done through the modern method and through the Haber process. It is a very unique process. Haber process, also called Haber-Bosch process, is an artificial nitrogen fixation process. Mandatory reaction because it is the main industrial procedure for the production of the ammonia today. It was discovered by the German physicists Fritz Haber and Karl Bosch, who developed it in the first decade of the 20th century. The process includes the atmospheric nitrogen, which converted into the ammonia by the reaction of the hydrogen using a metacatalyst under high temperature and pressure. So this is a brief intro of the Haber process manufacturing of two ammonia. Haber process is used to get ammonia. This is the summary. In Haber process, nitrogen and hydrogen are pumped out through the pipes having a pressure to pressurize the mixture of the gases up to 200 atmosphere, and pressurized gases are heated up to 450 degrees Celsius. Then it is passed through the tank containing an iron catalyst. Nitrogen and 1 mole of nitrogen which are comes from the air and 3 moles of hydrogen which come from the methane are reacted together and we get 2 moles of ammonia. And we also have condition for this. Iron catalyst is used for this. Alpha furate is used for this. So what are the sources of the reactant? Hydrogen and nitrogen are the source, are the reactant, and the source of hydrogen is from the methane, which is basically from the natural gas. The conversion steam reforming is conducted when the steam in the high temperature and the pressure tube inside a reformer with a nickel catalyst separating the carbon and hydrogen atom in the natural gas. So this is how we can gain the hydrogen. And the major source of the nitrogen is from the air. So, what are the catalysts that are used in this reaction? Hammad-Bosch process relies on the catalyst to accelerate the generation of the nitrogen. It is a homogeneous catalyst because the meaning of the solid that interacts on the gaseous reagent. Heterogeneous catalysts are those in which the phase of the solid means reactant and the catalysts are different. Here we also use the promoter. The catalyst containing promoter includes aluminium oxide, potassium oxide, calcium oxide, etc. And the catalyst composition which are used in this process is as follows. And why we use catalyst iron instead of others? Haber initially used the catalysts which are based on the osmium and uranium, but later on he moved to alpha ferrate or iron because due to its relatively low price, high availability, easy processing, lifespan, activity. So iron was ultimately chosen as a catalyst. What were the ideal conditions for this production of the ammonia? For highest yield, is theoretical produced by the low temperature and high pressure. In real condition, low temperature slows down the rate of reaction and high pressure is too costly. So we have to do the compromise. And how we did it? We have to higher the temperature, which are used to increase the rate of reaction by taking it up to 450 degrees Celsius. And we have to use the medium pressure up to 200 atmosphere. So what does Lee-Chatterjee principle say in this? It stated that if the stress is applied on the system at equilibrium, the system acts in such way so as to nullify or cancel as far as possible the effect of that stress. What are the ways to maximize the yield of the ammonia? Using the Lee-Chatterjee principle, we can use 3 ways to maximize the yield of the ammonia. The first one is continual withdrawal of ammonia. By using this, the equilibrium will shift toward the forward direction. By increasing the pressure, 4 moles of reactant combines to give 2 moles of product. High pressure will shift the equilibrium to the right to give more and more ammonia. Decreasing the temperature will shift the reaction into the forward direction according to Lee-Chatterjee principle. So high pressure, low pressure, and continual removal of the ammonia will give the maximum yield of the ammonia. The condition that was set for the compromising is temperature should be kept at 4 degrees Celsius, 400 degrees Celsius, pressure will be at 200 to 300 atmosphere, and catalyst will be a piece of iron catalyst which are embedded in the fuel mixture of magnesium oxide, aluminum oxide, and silicon oxide. It is of great economic importance because nearly 30% of the all nitrogen fixation on the earth is accomplished industrially through Haber process. So what are the formation steps? In the first step, there is the formation of the hydrogen. In this process, we're going to talk about the first step. Methane is reacted with water to give carbon monoxide and we get 3 moles of hydrogen. In the second step, there's the formation of carbon monoxide. Methane is oxidized and we get carbon monoxide and hydrogen. We did this step because we have to maximize the yield of the reactant, which is hydrogen. Because we can take the nitrogen from the air, but we have to gain the hydrogen from the reactions. So the third step is the carbon monoxide converter or water gas shift reaction. In this carbon monoxide is reacted with water and then we get carbon dioxide and hydrogen. It's highly exothermic. The fourth step is carbon dioxide removal. Carbon dioxide can be removed from the gas by gas scrubbing with triethylenamine. The fifth step is the compressor and the heat exchangers. The gas mixture is then compressed to the operating pressure by turbo compressor, and then it is sent to the heat exchanger. It is used to preheat the raw material. The fourth step is ammonia reactor. The actual production of the ammonia takes place in the ammonium reactor. The first reactor were bursting under the high pressure because the atomic hydrogen and the carbonaceous steel partially would combine to methane and produce crack in the steel. So the tabular reactor was best at that time. Bosch developed a tube reactor consisting of the high pressure bearing steel tube in which low carbon can easily be done with the catalyst. So this is how we get the ammonia. But there is a disadvantage of the tubular reactor, which was relatively high pressure loss. So, in the seventh step, the reaction product is continuously removed from the maximum yield. The gas mixture is cooled at 450 degrees Celsius in the heat exchanger using water, freshly supplied gases, and other processes steam. In the eighth step, the ammonia is condensed and is separated in a pressure separator. Unreacted nitrogen and hydrogen, which are the reactant, are then compressed back to the circulating gas compressor, supplying with the fresh gas and fed to the reactor, and then the ammonia is purified. So this is the flow chart of all the manufacturing process of the ammonia. Hydrogen and nitrogen in the reaction chamber are sent, and then it is compressed, and after that we give it a conditions of high pressure and high temperature, and then it is sent into the catalyst chamber where we provide it an iron catalyst to speed up the reaction with along with the promoters. Then there is an equilibrium chamber where the reaction nitrogen and hydrogen give the mixture of the ammonia at equilibrium state. Then we have to merge the mixture of gases from the reactor and cool it. Then the ammonia is liquefied and separated. But when the iron catalyst doesn't do its work, it is the unreacted nitrogen are turned back into the first chamber, and then the process again started. So this is the flowchart diagram. First, methane reacted with the water, and we get carbon monoxide and hydrogen. From air, we get nitrogen and oxygen. So here is the oxidation of the methane, and we also get carbon monoxide and hydrogen. So the gases will be carbon monoxide, hydrogen, and nitrogen. These three were the gases. And in this chamber, there is a catalyst, and there is a 500 degrees Celsius, and from there, the carbon monoxide reacted with the water, and we get carbon dioxide, nitrogen, and hydrogen gases. These gases are sent into the compressor where it's compressed and then sent to the scrubber where there is a removal of the carbon dioxide and the excessive water. Then after the removal of the carbon dioxide, the water is then added, and then all the gases means nitrogen and hydrogen is compressed and sent into the preheater where the nitrogen mixture of the gases is preheated. Then it is sent to the reactors where the catalyst is present as sulfurate, and the condition were given 450 degrees Celsius and 300 bars. Then there is the production of the ammonia, which are sent into this waste heat boiler, and then we get our reaction, and the ammonia is a product, and then we cool the ammonia, and all the unreacted gases means mixture of the nitrogen and hydrogen are sent back into the preheater to get back the ammonia again, and then ammonia is purified and liquefied. So these are the uses of the ammonia. Ammonia can be used as the manufacturing of the fertilizers. These include nitric acid, explosive, fiber, synthetic rubber, etc. Refrigeration for making ice, large scale refrigeration plant air conditioning units are being used. Pulp and paper extraction, metrology, etc. Which another method for the production of the ammonia is cyanamide process. Its a process type is of chemical product is calcium cyanamide, and the leading companies are Northwestern Cyanides companies, and the years are from 18 to 95 in 18 to 99 invention. Developer are Adolf Frank, Nicodem Caro. So what is this process? The Frank-Caro process is also called cyanamide process. It is the nitrogen fixation reaction of the calcium carbide with the nitrogen. in the reaction vessel at about 1000 degrees Celsius. The reaction is exothermic and self-sustaining once the reaction temperature is reached. This is calcium carbide. When it is reactive with the nitrogen, it gives cyanamide plus carbon monoxide. And when the calcium cyanamide reacted with the water, it gives calcium carbonate along with the ammonia. So this is how we get our ammonia as a product. Thanks all. That's all from my side.